Okay, this is going to be the lecture over the final section, section 18.7 in chapter 18. We're going to be talking about dielectrics. Now, if you don't know exactly what those are, you're going to be looking at a combination of two different types of materials. And rather than have the space between the plates of the capacitors filled with vacuum or air, we're going to put this substance in between it. And what we want to know is how does the configuration or the attributes of the capacitor change when we do that. So when that space between those conductors in the capacitor, the upper plate and the lower plate, is filled with this dielectric material, the capacitance is going to increase by a factor of K, and that's going to be called the dielectric constant of the material. We'll go through that here in just a little bit. When the charges plus or minus Q on the plates remain constant, the charges that are induced on the surface of the dielectric material decrease the overall electric field and potential difference between the conductors by that same factor. Now, under sufficiently strong fields, dielectrics become conductors, and that's going to be called dielectric breakdown. The maximum field that a material can withstand without breakdown is going to be called its dielectric strength. So let's go through this particular section here and try to flesh out what these ideas are. So most capacitors are going to have a non-conducting material or a dielectric between the two plates. A common type of capacitor will use two strips of metal foil for the plates and two strips of plastic sheet, something like mylar. And it's going to be like this. You can see you've got a plastic sheet here, and then you've got the conductor. So you've got that situation here, and then you just kind of sandwich it together. Now, it serves three functions to do this. It's going to solve the mechanical problem of maintaining two large metal sheets at a very small separation without actual contact. It's going to make it more sturdy. The second is when it's subjected to a sufficiently large electric field, any material, any dielectric material is going to undergo dielectric breakdown. And that's a partial ionization that permits conduction through a material that is supposed to be an insulator. So solid dielectrics can tolerate stronger electric fields without breakdown than air can. So it's to our advantage to have that there. The third thing is that the capacitance of a capacitor of given dimensions is going to be greater when there is a dielectric material between the plates than when there is just air or a vacuum. And we can demonstrate that effect with the aid of an electrometer, a device that measures the potential difference between two conductors without letting any appreciable charge flow from one to the other. So we've got that situation going here. We've got an electrometer that connects to both of those charge plates, and then there's going to be a vacuum between it. We're going to measure that potential difference, and it turns out to be V sub naught. When we insert a sheet of dielectric between the two plates, the potential difference is going to decrease to a smaller value. In other words, the voltage is going to drop when we put this dielectric material between the two. So when you remove it, the potential difference returns to its original value, showing that the original charges on the plates haven't changed. It's just the potential difference that dropped. So the original capacitance is going to be again, the capacitance is going to be Q over V. So we know what that original voltage is, so we can determine what the capacitance is. Now, the capacitance with the dielectric is going to be that reduced voltage. Now, the charge is going to be the same in both cases. This value is going to be less than this. Now, when you take the same number, Q, and you divide it by a smaller number than what you did before, guess what? That is going to increase in value. That increase in value, if we take the capacitance and divide it by the original capacitance, you're going to get a dielectric constant. And depending on the material, that constant is going to be different. Now, since, and this is going to be an application of this, Since capacitance is inversely proportional to the distance between the conducting plates, one limitation on the design is going to be how thin the dielectric layer can be made. Right now, we are using a vacuum deposition or some kind of thermal spray technology, and that forms ultra-thin alternating layers of conductor and dielectric. And we can create layers as thin as 90 nanometers in these supercapacitors or nanocaps. And that allows significant increase in energy density. And such capacitors are currently used in defibrillators, which is what you're seeing here, and they'll be useful in applications such as very long-term energy storage during advanced space exploration. So it does have a use. Now, when the charge is constant, the potential difference is going to be reduced by a factor of K. Now, where does that come from? Well, if we take a look at this formula right here, if the capacitance is going to increase and the voltage is inversely proportional to that, then if we move the K over here and this over here, we can see that the potential difference is going to be reduced by that factor. Capacitance goes up, the voltage goes down. So the value K is going to be a pure number. It doesn't have any units with it. Since the capacitance is always going to be greater than what you originally had, then K is always going to be greater than 1. Some representative values of K are going to be given here in this particular table. For a vacuum, K is going to be equal to 1. For air at ordinary temperature and pressure, K is going to be equal to, it's roughly 1, but it's going to be a little bit more than that. So for most purposes, a capacitor in air is going to be equivalent to 1 in vacuum. When you insert a dielectric material between the plates of a capacitor while the charge is kept constant, potential difference between the plates decreases by a factor of K. What that also means is that the electric field between the plates must decrease by the same factor. Remember this formula back here? You may not. I had to look it up myself. The electric field is going to be equal to the change in the voltage divided by the change in the distance as the point moves perpendicular away from an equipotential surface. Since this is directly proportional to this, it shouldn't surprise you that this situation is the same as this. So the fact that E is smaller when the dielectric is present means that the surface charge density is also smaller. The surface charge on the conducting plates doesn't change, but an induced charge of the opposite sign appears on each surface. So you can see here you've got the positive plate here. It's inducing a negative charge here, and the negative plate over here is inducing a positive charge here. So this surface charge is a result of the redistribution of charge within the molecules, and it's a phenomenon called polarization. So you've got some problems here to work through. Now, dielectric breakdown. We mentioned earlier that when any dielectric material is subjected to a sufficiently strong electric field, it becomes a conductor, a phenomenon called dielectric breakdown. So the conduction occurs when the electric field is so strong that electrons are just basically ripped loose from the molecules and they crash into other molecules. And that liberates even more electrons. And that avalanche of moving charge forms a spark or arc discharge. And it's pretty sudden. If we're going to take a look at a couple of these. One's in laboratory and the other's in nature. If you see something like this is going to be a block of plexiglass that's subjected to a very strong electric field. And then you can see as the electrons go through, they break loose, breaking through others, and then eventually form sort of a chain as it goes through the entire material. Same thing holds true here for lightning. What you are seeing here is charge that eventually just ends up flowing from one spot to the other. So capacitors are always going to have a maximum voltage rating. When a capacitor is subjected to excessive voltage, an arc may form through that layer of dielectric, and then may burn or melt a hole through it. And that hole provides a new conducting path between the conductors, and basically you've got electrons going where you may not have intended them to go in that fashion. And if the path remains after the arc is extinguished, then you've got a busted capacitor. The maximum electric field that a material can withstand without the occurrence of breakdown is going to be called your dielectric strength. And then the dielectric strength of dry air is about 3 × 10⁶ volts per meter. And for common insulating materials, range somewhere between 1 to 6 × 10⁷, all substantially greater than that for air.